Hey everyone, so this is going to be the third and final video in this basic forces unit where we're going to actually talk about friction. Now remember, friction doesn't always occur. There are only certain scenarios where we're dealing with friction, so try to keep an eye out for that. We've already kind of talked about how we can find friction using FNet and FBDs, but now we're actually going to come up with an equation. Now, the big thing is, what is friction? As I said, I kind of briefly went over it before, but friction is something that we say always opposes motion. Now, there's one thing I want to clarify in this. If an object is moving to the right, friction will end up be going to the left because it will oppose that motion. However, there is another aspect to that statement. If an object is being pushed to the right but not moving, so it's still at rest, friction will still oppose the attempt of moving to the right by also acting to the left. So even though we say that friction always opposes motion, that doesn't necessarily mean that the object has to be moving for friction to exist. Friction does also exist on objects that are at rest as a way of keeping it from moving in whatever direction it's going. So kind of keep that in mind as well. Now, the whole point of friction and where it actually comes up from is that it's coming from the rubbing of the two surfaces. In particular, if you actually looked at two surfaces under a microscope and at a very fine look, you'll notice that all surfaces have these little bumps and divots and grooves in them. So when you have two surfaces and their bumps and grooves kind of interact, they end up interlocking with each other, and that's what's actually causing for the trouble. The bigger those bumps, the harder it is to rub these two surfaces together. The smaller these bumps or the smoother those two surfaces are, the less friction you have. So that's pretty much where it's coming from. It's coming from the bumpiness, the rigidness of the bumps kind of coming together and rubbing against each other. Now, there's two different types of friction, and it kind of goes back to what I said about how friction can oppose motion. The first type that we have is static friction. So this is the friction that objects feel when they're at rest. So if you have an object that's motionless, you try to push it to the side, but it doesn't move right away. That's because of static friction. Um, and then kinetic friction is what happens when you have an object already moving that's sliding across the surface. And again, friction's there to kind of oppose it. So we have static friction where the object is at rest feeling friction, and an object that is moving feeling kinetic friction. Now, the equation we have for friction is given on the reference table. It's Ff equals mu Fn. So this symbol here is called a mu. It's a Greek letter. So F of F is the force of friction, we all know that, and F of N is the normal force. Try not to get Fn and Fnet confused. This is the normal force, and the other one is the frictional force. Also note that both of those forces are measured in newtons. So when you record this into your notes, make sure that you notate that these are both in newtons. This mu term is what we call the coefficient of friction. Um, a little bit about that in a second, but I just want to clarify. So the reason why Fn is in here is because going back to the whole idea about the bumps kind of being interlocked with each other, uh, if you have two surfaces that are really, really tightly connected and pushed together, they're going to feel a lot more friction than if they were just slightly touching each other. You can actually see this yourself. Take your hands, start rubbing them together. If you kind of just gently kind of put your hands together and rub, you'll kind of feel a little bit of heat. But if you push really hard, you'll notice that every time your hands slide across, you'll generate a lot more heat with a lot more force being applied. So that's kind of why Fn is in that equation. Now, going back to mu, the coefficient of friction, it's basically a statement of how rough the two materials are that are rubbing. And it's always about two materials. You don't have the coefficient of friction of rubber, it's always rubber on concrete or rubber on ice, because those two surfaces will always interact differently. Rubber acts differently on ice than it does on concrete. But if you have a high coefficient of friction, that usually means that the two surfaces are really hard to rub together. For example, rubber and concrete have a very high coefficient of friction. If you have rubber material, it's not going to slide very easily across the concrete because of the bumps and grooves. On the other hand, low coefficient of friction would normally mean that it's easier to rub. So something like ice on rubber or ice with metal tends to have a very low coefficient, so it's going to slide very easily. Now, one question that could be asked is, what are the units for mu? So if we look back into the equation, we have FF equals mu Fn. If we look at the units, the frictional force is measured in newtons, the normal force is measured in newtons. That means the unit for mu is nothing. There are no units for mu. So it's the one of the few numbers where you actually don't put a unit next to it. You can see this because there's actually a table on your reference table of all the coefficients of frictions. It's on the front page, bottom right. You'll notice none of those numbers have units, basically because mu has no units. Now there's two different types of frictions, meaning that we're going to have two different mu's. The equation's the same. What's different is the mu term. So if we're trying to find static friction, we're going to use what's called the static coefficient of friction. So we use mu s for when the object is not moving. If the object is moving, then we're going to use the kinetic coefficient of friction. So again, the equation doesn't change. It's just that mu term that we plug in. And again, you can see that on the reference table that there's two columns for each of the surfaces. There's a kinetic side and a static side. Now, one thing to note is that when you use the static side, it always gives the maximum force that can be applied in order to keep the object at rest. What I mean by that is if you use these numbers, let's say, and you find that when you plug in the static coefficient of friction into the mu Fn equation and you get that the static force is 4 newtons, that means any force applied onto this object that's less than 4 newtons, the coefficient of friction or the frictional force will end up balancing out. So if you have a 2 Newton force applied to it, the frictional force will be 2 newtons. If you change this to 3 newtons, then the frictional force will bump up to 3. Since it's still less than 4, it will keep this at rest. Even if you apply 4 newtons of force to the object, the frictional force will balance that with 4 newtons. But the moment you apply just a little bit more than 4 newtons, the object will begin to move because friction can no longer keep it in place. This is actually one of the reasons why you sometimes find yourself slipping, is because what ends up happening is the force that you're applying is too high and the frictional force can no longer hold it in, and instead of keeping you at rest, you end up sliding and moving. So I just want to point this out, that when you use mu Fn for static forces, it only really tells you the maximum force you can apply. All right. This kind of goes with what I said before, is that you don't really need to memorize any of the coefficients. You have them on the reference table. The only thing that is important to remember is that the static coefficient is always greater than the kinetic coefficient. This is one of the reasons why it's always harder to start an object moving than to keep it moving. So if you try to push your dresser, it requires a whole lot of force in the beginning, but once you get it sliding, it becomes a lot easier to continue the sliding all around. And that's because of the whole static coefficient being higher than the kinetic. All right, and this just says what I said before. All right, so here are some questions. Pause the video, work itself. We'll go over in a second. All right, so here they want to know which two surfaces require the greatest applied force to get on the slide. If you look on the reference table, we look for the one with the highest coefficient, and that would end up being rubber on dry concrete. And that's it. Here's the next one. Pause the video, work itself. We'll go over in a second. All right, same thing. Here they want the smallest force. So I'm going to look on the reference table. find the one with the smallest coefficient, and it ends up being Teflon on Teflon. Or you could also say wax skis on snow, since they do have a roughly the same coefficient. But both of those surfaces would be pretty much the least amount of force needed to get them to slide. All right, here's the next question. Pause the video, work itself, and we'll go over in a second. All right, so here, if we listen to the last sentence, compared to the force required to start the box moving, the force required to keep it moving is less. It's always less to keep it moving than it is to start moving, and that's because of that coefficient. Here's the next question. Pause the video, work itself, and we'll go over in a second. All right, so here, if I start doing an FBD, I have a box, I have 12 newtons applied to it, and I know that friction is going to be acting in the opposite direction. Now, the fact that the box remains at rest tells me that I'm in equilibrium. Equilibrium means balanced forces, so if it's 12 newtons to the right, that means I have 12 newtons to the left. And that's it. Remember, you don't always have to use an equation. Sometimes you just use Newton's laws with the equilibrium in order to figure it out. So kind of keep that in mind. All right, here's the next question. Pause the video, work itself, and we'll go over in a second. All right, so this is the same one as before. We have a box. We have 16 newtons applied to the right. We have friction to the other side. Once again, it's in equilibrium because it says the phrase constant speed. So if it's 16 newtons to the right, then it's 16 newtons to the left. Next question, pause the video, work itself, and we'll go over in a second. All right, so here we're going to go into a little bit more detail. So once again, I'm going to draw an FBD. Now this time I'm actually going to want to go into a little bit more detail with my FBD. So we have a 18 Newton force being applied. We're going to end up having friction to the left. Because it says that it's constant speed, I know that these forces have to be balanced. Now that answers this question of what the force of kinetic friction is. It's going to end up being 18 newtons. But because I have another part, I want to finish off this FBD. So there's force of gravity pulling it down. And if I read the question, it says the box is 20 newtons. So because of the fact that it's newtons, I already know that this is my force of gravity. Because it's on a horizontal surface, the tabletop, there's also going to be a normal force, which in this case will also be 20 newtons because the normal balances out the gravitational. Try not to get into the habit of thinking that Fn equals Fg. Fn equals whatever is opposite it. So because Fg is opposite it, then it's equal. But you will see cases where Fn is not opposite Fg. So try not to get into that habit. It's a bad habit that you're going to have to break. So if I go down to part B, they want the coefficient of friction. Because they don't tell me the material involved, that means I have to use the equation. Ff equals mu Fn. The force of friction is 18 newtons, and the normal force is 20 newtons. So we just do 18 divided by 20, and we should end up getting 0.9 as my coefficient of friction. And remember, there are no units involved, so it's just 0.9. All right. Most of the time, the coefficient should be less than 1, but it doesn't. I don't think it has to be less than 1. All right. Here's the next question. Pause the video, work itself, and we'll go over in a second. All right. So once again, kind of want to just do the whole FBD. So we have this. We have force of gravity pulling it down. Now it tells me that the block is 20 kilograms. Again, the unit is in kilograms. So I'm going to actually have to calculate the weight by doing Fg equals mg. The mass is 20. And the gravitational acceleration is 10. So Fg is going to be equal to 200. Since gravity's pulling it down, the force of gravity is pulling it down, and it's on a floor, there's going to be a normal force pushing it up, which, because they're opposite directions, will be 200. Person's pushing it, doesn't really, oh, it's he's pushing it to the left. And then there's a frictional force to the left, sorry, to the right. So if I read part of B, they want the force of the floor acting on the crate. We already found that that's going to be 200. And then the maximum force that could be applied before it moves. So this is the applied force that they're looking for, but because it's going to be at equilibrium, it says that it attempts to move, and it's also saying before the crate moves. So this crate's at rest, meaning the applied force is equal to the frictional force. So I'm going to use mu Fn. I'm going to look on the material list to find the static wood on wood. And static wood on wood is 0.42. And my normal force is 200. So when I plug that in, I end up getting 84 newtons. So the maximum force that can be applied on this crate is 84 newtons. Any higher, this object will start to move. All right. Here's the next question. Pause the video, work itself. We'll go over in a second. All right. So here they want us to draw an FBD. Again, we had the force of gravity pulling it down. It says that the crate is 20 newtons. The unit is newtons, so I don't have to do anything with that. I just plug it in as 20. There's an Fn going up, because again, it's on a flat horizontal surface. There's an applied force to the right. There's a frictional force to the left. And it's constant velocity, which means forces are balanced. So I have my FBD drawn. They want the frictional force on the object, so FF equals mu Fn. We have a asphalt and rubber, or dry asphalt and rubber. So that's going to have, and it's moving too, so that's going to be the kinetic, which is 0, there it is, 0.67, and the normal force is 20. So when I plug that all in, I end up getting a frictional force of 13.4 newtons. And again, because of the constant velocity phrase, if the frictional force is 13.4, then the applied force is 13.4. Always keep an eye out for that phrase, constant velocity or at rest, because they're going to be your best friends. They're going to tell you that everything's balanced. It's going to make life easy, because it's just going to be addition, subtraction, setting things equal to each other. Easy stuff. All right. Here's the next question. Pause the video, work itself, and we'll go over in a second. All right. So back to here. Again, kind of want to draw an FBD just to be safe. So force of gravity pulling it down. It's 16 kilograms. That's not in newtons, so I have to do Fg equals mg. Multiply 16 by 10. And I get that it's 160 newtons. The normal force is pushing up with also 160 newtons of force. It's pushed along the floor. It's going to be applied force of 50 newtons. So over here it says that the magnitude of the frictional force, so there's going to be a frictional force. Now because they don't say that magical phrase, I can't assume that these are equal. So I'm going to have to calculate the frictional force using mu Fn. They give me enough information saying it's rubber on ice. So I'm going to go to rubber on ice. There's only the kinetic one, so clearly this is a moving scenario. So 0.15 times 160 is 24 newtons. So the frictional force acting on this block is 24. newtons. Now, if I get to part C, it wants to know the magnitude of the net force. Remember, net force is just us adding these forces up, or in the case of this scenario where we have forces going in different directions, we're going to subtract them. So the 160 and 160 cancel out. So I'm going to do 50 newtons minus 24 newtons. And I get that the net force is going to be 26 newtons. If I want to be a little bit more specific, I would say based off of my diagram it's right, but I just realized that the question doesn't specify the direction, so I wouldn't actually be able to say that. It's whatever direction the object was applying the force. And that's pretty much it. So one thing that I want to point out is you'll notice that you have to do MUFN. If you start to notice that they go into a little bit too much detail about what materials make up these objects, you should notice by now that a lot of the questions remain vague. We're always talking about an object, a block, a crate, something very, very generic. But once you start seeing it being described as a wooden crate on a rubber surface or something like that, that should kind of let you know that, okay, we're probably going to end up using MUFN at some point, and you're going to be using that box. In fact, there are certain materials that you'll see a lot. Rubber on concrete, wax skis on snow, the ice one, wood on wood is another big one. You might see Teflon on Teflon, but you see these a lot. There's not really that many of them. So kind of keep an eye out for that. But just remember, just because they ask for friction doesn't mean you have to use MUFN. All right, if you have any questions, let me know. Otherwise, I'll see you later.